Well, thank you for that nice introduction, and it's really great to be here today. Let me give you just a quick outline of what I'm going to be talking about. I'll start with some definitions just to make sure we're all on the same page. I'll talk about what's wrong with business as usual, at least the way I see it. And I'll talk about what is a multi-phase optimization strategy, what I mean by optimization. Okay, how do you do this? I'll give you an example of a project that's in the field, and then we can maybe imagine a few things. So definitions. So I think everyone here knows what a behavioral intervention is, or we probably have the same definition in mind, because I know you folks do a lot of behavioral interventions, but just so we're all on the same page, I'm going to define a behavioral intervention as a program aimed at modifying behavior for the purpose of treating or preventing disease, from promoting health, improving academic achievement, and or enhancing well-being. But this is what's really important, is that most behavioral interventions are made up of multiple components. And as you know very well, a behavioral intervention is not like a pill that you give someone and they swallow it and that's the end of the treatment. Every behavioral intervention has a lot of different components, or what you might think of as moving parts. So what do I mean by an intervention component? Well, I define that as any aspect of an intervention that can be separated out for study. So what's a component is kind of in the eye of the beholder. But what I want to point out is that although if I mention an intervention component, probably the first thing that pops in your mind is a part of the intervention content. So if you have an intervention where you're covering a number of different topics, maybe a school-based drug abuse prevention program where there might be some lessons on resistance training, there might be some lessons on adjustment of normative expectations, there might be some lessons that bring the parents in. So each of those potentially could be a component. But a component can also be a feature of the intervention that promotes compliance or adherence. So if there's medication involved, maybe having MEMS caps could be a component. Or could be a feature aimed at improving fidelity of delivery of the intervention. So maybe an 800 number that program delivery staff could call if they have questions. So intervention components can be any of these things. According to this definition, some of the components may be pharmaceutical. So if you have a HIV prevention program that involves PrEP and also has some behavioral components that are intended to promote adherence to PrEP, I would still, by my definition, still call that a behavioral intervention. And components can be defined at any level. So they can be defined at the level of the individual participant, but also you might think of a more structural intervention that would be defined at the school or community level, family level, clinic level, any level. And this is maybe obvious, but I think is worth saying that an intervention component can have an impact on efficacy, effectiveness, and or cost effectiveness. Okay, so those are the few quick definitions. What's wrong with business as usual as I see it? Well, let's talk about what constitutes business as usual. Here's how behavioral interventions are typically developed and evaluated, and I'm sure that this will be familiar to most of you. So you have a set of intervention components that you're considering for inclusion in the intervention, and you choose them based on scientific theory, clinical experience, possibly secondary analyses you've done on data you or others have collected, and so on. And then once you've identified the components you want to include, they're assembled into a package, and then that package, as a package, is evaluated by means of a standard RCT, usually a 2-arm RCT where there's a treatment arm and a suitable control or comparison arm. So we're going to call this the treatment package approach. It sort of doesn't have a name because it's just what everybody does, and so for that reason it evidently has never been named. But we're going to be comparing it to another approach, so we'll call it the treatment package approach today. Okay, so here's a schematic of the treatment package approach. You might have a set of components, you assemble them into an intervention, and then the intervention is evaluated by means of an RCT. And I deliberately chose black for this box because once you assemble the components in here, you don't know what's going on inside the box. You don't know which of the components are operating. You don't know if some of them are inert or some of them are working great, and maybe some could even be in the minus column. So What's wrong with evaluating a treatment package by means of an RCT? I want to make this clear that there's absolutely nothing wrong with that. And I don't want anyone to get the impression that I'm anti-RCT, because I'm definitely not anti-RCT. And you'll see in a few moments that the RCT actually is a part of the multi-phase optimization strategy. The RCT is a great design when it's applied the way it was meant to be applied. So the RCT is suited for determining whether a treatment package performs better than whatever you're comparing it to, standard of care, perhaps an alternative intervention. So it's great for that. But it was never intended to do everything, which is kind of what we've been asking of it for the last 20 years or so. My problem is right here. It's with what happens between identifying a set of components you're interested in and assembling a behavioral intervention. So let's go back to the RCT for a second and think about what can the RCT tell us and what can it not tell us. Well, suppose you have a treatment package you're interested in, you subject it to an RCT, and yahoo, you have a significant RCT. So now, what don't you know? You don't know which components are making positive contributions to the overall effect. It's possible that some of them are doing nothing. It's possible even that everything is due to one component and you could just ditch the others. You don't know. You don't know whether the inclusion of one component has an impact on the effect of another, and that can go either way. The inclusion of one component can enhance the effect of another component, or it could undermine the effect of another component, and we don't know that. You don't know whether a component's contribution offsets its cost. It's interesting to me that we almost never ask that question, and yet some components in an intervention might be really cheap, and so throwing them in is not a big deal. Others might be pretty expensive, and you might expect that you might desire that the more expensive components have a larger effect in order to offset that cost. You don't know whether all the components are really needed. Isn't it a shame to think of time and energy, both on the part of the participants and the part of the people administering an intervention, all that time and energy and money wasted on components that might not really be needed? And in general, you don't know how to make the intervention more effective, efficient, or scalable. And that's another question we don't ask that often. Once we have a significant RCT, it's like, okay, we have an intervention that works, we're not going to mess with it. Instead of thinking more in terms of improving interventions in an incremental fashion over time. Now suppose you get a non-significant RCT. That's really bad because you know even less. You don't know whether any of the components are worth retaining. It could be that there's one or two really good ones in there that you'd like to keep. You don't know whether one component had a negative effect that maybe offset positive effects of others. If you have a lot of components, if you've got a few in the plus column and a few in the minus column, you can end up with a net zero. You don't know. And what's most frustrating, I think, is that you don't know specifically what went wrong, and you don't really have that many leads for how to do it better the next time. So in general, if you get a positive RCT or a null RCT, you don't really know what the next steps are to do better the next time. So what's the alternative? Well, think about consumer products over the last 20 or 25 years versus behavioral interventions over the last 20 or 25 years. Consumer products have made a lot of progress over the last 20 or 25 years. Even vacuum cleaners today are not what vacuum cleaners were 20 or 25 years ago, just to take a sort of trivial example. And the reason for that is that there's a different mindset about development of those products. So when engineers build products, they take a quite different approach to the approach that we take as intervention scientists. They take an approach that's very systematic, that emphasizes efficiency of the approach and also efficiency of the product. And that's focused on the clear objective of optimizing the product. I'm going to talk more about what I mean by that. So the multi-phase optimization strategy, which is what I'm here to talk with you about today, integrates these methodological perspectives from engineering and also from the behavioral sciences. The situations we're in in the behavioral sciences and intervention sciences. Not the same, of course, as the situation an engineer is who sets about to develop and improve vacuum. And I don't at all mean to trivialize the difficulties of, that people face in intervention science by saying we can do it exactly the way an engineer does it, is working on a better ball bearing. But we can take some ideas from that approach and build optimized behavioral interventions. So what is MOST and what is optimization? So MOST is an engineering-inspired framework for development, optimization, and then evaluation of behavioral interventions. And I want to emphasize this, that using MOST, you can engineer an intervention to meet a specific criterion. And I'm going to talk in a minute about what I mean by that. So here's a schematic of the multi-phase optimization strategy. So you start with a set of components, and I keep using 5, but it doesn't have to be 5. And instead of going directly to here, you go through another experimental phase of empirically based optimization. I know that seems abstract, but I'm going to get much more concrete about that in just a moment. And in this empirically based optimization, you do experimentation to evaluate the performance of individual intervention components and also to assess whether there's interactions between intervention components. That's the part about a component possibly enhancing or undermining the effect of another one. And so once you understand all that, you can put them together to form an optimized intervention. And notice I've used a transparent box here because as opposed to the treatment package approach, in MOST, you know what's going on inside the box. And then you can evaluate this treatment package by means, this optimized treatment package, by means of a standard RCT. So empirically based optimization gives you this nice transparent box that you then would evaluate by means of an RCT. MOST is a very different mindset. It's a very different approach to development of behavioral intervention. So the logic here is really not to identify the one best combination of intervention components. So let's say you had 5 intervention components that you were interested in. If you were to make up, and let's say that each of them had 2 levels, maybe could be included or not. Those are the 2 levels. If you were to make up every possible combination of those, there would be 32 different combinations. And the only way to get, the only way to pull out, to identify the one best would be to do a 32-arm RCT, and it would have to be powered sufficiently even to detect a small difference between maybe the best one and the second best one. So no one's ever going to do that study, right? So let's just forget about that as an alternative. So instead, MOST sets a more modest goal for itself, which is to identify one of the 2 or 3 best combinations. So the idea is to weed out all the clunker combinations in there and identify one of the 2 or 3 best approaches. And you do this by selecting an approach to experimentation using the resource management principle. So here's the resource management principle, and this applies to selecting an experimental design for assessing the individual effects of the intervention components. The resource management principle just says you conduct research in such a way as to get the most information you can given the resources that you have available to you. So with the resource management principle, you start by a clear statement of what you need to find out, and then a clear assessment of what are the resources you have or can reasonably get. So a reasonable budget you could put into a grant proposal, say. And then you ask the question, how can I manage my resources strategically to find out what I need to know? And this will mean sometimes using a design other than the designs that you might be most familiar with. So you have to decide what information is most important and target the resources there. The emphasis here again is on very efficient experimental design, so trying to just squeeze the most information you can out of the money you have. And sometimes this will mean taking calculated risks to move science forward faster. And I'm going to give you an example of that in a moment. So a lot of times, the first question people have for me about most is, can I do it in a normal NIH budget? And I always say yes, because the starting point is the resources you have or can reasonably get. So you don't, with most, you don't say, well, I need to find out X, Y, and Z, and I need to do it this certain way. But to do it that certain way would be so expensive, and so therefore I'm not even going to bother with it, which is a logic that some people have that takes them back to the RCT sometimes. Instead, the idea is, I have these resources, I need to find this out, and I'm going to do what I need to do with the resources that I have. So by definition, most does not require an increase in resources, but you may find, if you start seriously considering most, that you're actually devoting resources, you're spending the resources in different ways, so it might require reallocation. And I know this seems abstract. We're going to get more concrete in just a moment. So most has 3 phases: preparation, optimization, and evaluation. The preparation phase, with one exception, is stuff you all already do. So the idea here is just to lay the groundwork for the optimization you're going to be doing later. So you do stuff like review prior research, take stock of your clinical experience, and so on. Derive a theoretical model. This is really important, as detailed as you can possibly get it, that expresses the process of the health behavior that you're interested in intervening on, and that shows ultimately how the components you're selecting are expected to impact that process. Based on the theoretical model, you select intervention components. You would do any pilot work would be done here in the preparation phase. And this is the one that's different, and I'm going to spend a few minutes talking about this. Identify a clearly operationalized optimization criterion. So now let's talk for a moment about what we mean by optimization. I just got this out of the Concise Oxford Dictionary of Mathematics online. Optimization is the process of finding the best possible solution subject to given constraints. So when I talk about using most to develop an optimized intervention, I'm not in any way suggesting that that if you use most, you'll develop the best intervention anybody could ever get. What I'm suggesting, though, is that you can use it to develop the best intervention you can get subject to the constraints that you have on hand. And I'm going to show you a little bit more about that in a moment. And I really like the concept of optimization because I like the idea of including constraints. An issue that I have with intervention science today is that those of us who are academics interested in developing behavioral interventions often, one of our objectives is to get a significant RCT. And so we end up adding a lot of components to the intervention, and the idea being to bump up the effect size. So we don't think ahead to it going to scale that much. And so, yahoo, we have a significant RCT, and then we hand it to someone else for it to go to scale, and what happens? It's too big, it's too complicated, it's kludgy, and so the people who are implementing the intervention, what do? They start removing parts of it. They say, oh, we can't do all of this, so we're not going to do this part, we're not going to do this part. Or people are saying it's too complicated, so we're removing this, we're removing this. Because we don't know what the active ingredients were to begin with, we don't know if what they're removing is the active ingredient. So in intervention science today, the difference between efficacy and effectiveness is huge. And I feel that if we built some of those constraints at the other end in at the beginning, I often say to people, start at the end, think about what the constraints are going to be, and then build it in. So optimization always involves a clearly stated optimization criteria. Now let's talk about a few optimization criteria, and you'll see, I hope you'll see what I mean by starting at the end. So the optimization criterion is your definition of just best possible given constraints, and it's a specific goal you want to achieve in the optimization. And one point I like to make about this is that once you achieve a particular optimization criterion, then that's a bar that's set, and in the future you can try to exceed that in an incremental way. So I'm going to go over very quickly 3 possible optimization criteria. So this is not my favorite optimization criterion because I feel like it's a little bit inelegant, but at the same time, it really resonates with intervention scientists in a lot of ways, and I can definitely see why. So just an efficient intervention with no dead wood in it. So just an intervention where all the components are contributing something toward the positive effect you want. So consider clinic-based intervention to increase adherence to PrEP. Maybe the investigators just simply want to be confident that every component is necessary. That at least they can say, we're not wasting any time and money in this. So you can achieve this by conducting the kind of experimentation I'm going to talk about in a minute and selecting only active intervention components for inclusion in the intervention. So here's another one that I think makes it a little clearer, the idea of constraints. The most effective intervention that can be delivered for some upper limit on cost. So suppose now, back to the PrEP intervention, suppose insurers say they'll pay for a program that costs no more than $125 a person to implement. So you can say, okay, I'm going to develop an intervention that's the most effective we can get that can be delivered for less than or equal to $125 a person. Now, time. That also could be an important constraint. In clinic settings, a lot of times, time is an important constraint. A lot of other settings, too. So suppose the clinic staff say, well, we have the best chance of delivering, of implementing this program exactly the way you intended if it takes no more than 30 minutes to deliver. So you can select a set of components that will give you the most effective intervention you can get that takes no more than 30 minutes to deliver. So this is what I mean by starting at the end. Starting at the end saying, what are the constraints on implementation? So there's lots of other possible optimization criteria. Cost effectiveness is one that's a little different from an upper limit on cost. You can use a criterion based on a combination of factors. You might, if you're interested in participant burden and assuming that can be quantified, you might be interested in putting an upper limit on that. Lots and lots of other possibilities. These are just some examples. So that was preparation. So now optimization. The objective here of this phase of research is to form a treatment package, an optimized treatment package. So I'm going to spend some time talking about exactly how you do this in just a minute. But the idea here is to conduct experimentation and then analyze the data. And that gives you the information you need about the effectiveness of each intervention component. And then based on that information, you'll use that information to select the components and component levels that will build an intervention that meets the optimization criterion. And then evaluation, that's simply the RCT that you're familiar with. Once you have the treatment package, you can evaluate it by means of a standard RCT. I want to take a moment to compare and contrast evaluation and optimization because they're both important, but they're not the same thing. So evaluation, this is a question you're pretty familiar with, I think. Is the intervention's effect statistically significant? You could put clinically significant in there, of course. Optimization poses a different question. Is the intervention the best possible given constraints? And you see that all four of these are possible. So suppose you evaluate an intervention, it's not statistically significant or not clinically significant, but it's not been optimized. So you could optimize it using effect size as a criterion. It is possible to include effect size in there as one element of the criterion. However, suppose it's not statistically significant, but it has been optimized, and that is possible. Just because you optimize an intervention, it doesn't necessarily mean that it's going to have a statistically significant effect. Now, think of the constraint on 30 minutes to deliver an intervention. It could be that given the components that you have that you're working with, maybe there isn't a way to get an effective intervention that takes less than 30 minutes to deliver. So sometimes that happens. And then you might want a different intervention strategy. Or you might want to change the criterion. This is where we are with most of our behavioral interventions today, I think, our evidence-based interventions. Been evaluated, been shown to be statistically significant or clinically significant, but has not been optimized. And so it could be more efficient, could be possibly more potent. And this is what I would love to see us aim for, interventions that have been optimized to a clear optimization criterion and have been demonstrated to have a significant effect. Okay, so now, I know that was pretty abstract, but let's talk in more concrete terms about, I have several funded projects that are using this approach. So some of you may know Bonnie Spring. She's at Northwestern University, and we're co-PIs on this study. It's to develop a highly effective weight reduction intervention that can be delivered for $500 a person or less, and it's funded by NIDDK. This is the theoretical model, which I actually would love to see this be more detailed, but this is the one that we put in the grant proposal. So there's a core intervention that everybody got. Really what we're interested in here is adherence. So really this is about getting people to do what they're supposed to. It's not really about the intervention itself, it's about getting people to do the stuff they need to do. So we're looking to affect adherence, which we expect will lead to weight loss. And we're looking to directly impact these social cognitive mechanisms: self-efficacy, self-regulation, supportive accountability, and facilitation. And we have these 5 intervention components that we're looking at. Phone coaching, people could have 12 or 24 sessions. Text messages, people either got them or not. Communication with the primary care physician, either that happened or not. Buddy training, everyone has a buddy. But the question is whether the buddy gets special training or not, and how to be a good buddy. That's about the supportive accountability thing. And then meal replacements, whether meal replacements are recommended, and they're kind of coached on using meal replacements or not. So this is a schematic of how this is implemented in this study, which we call opt-in. Here are the 5 components. We have the component screening experiment, which I'm going to talk about in a moment. We have the optimization criterion that we're using. And then based on the results of the screening experiment and consideration of the optimization criterion, we'll build an optimized treatment package that then will be evaluated in an RCT. We did not propose an RCT as part of the R01 that supports this, however. So that would be a future study. So the component screening experiment, that's obviously an important part of this. So the purpose of the component screening experiment is efficient screening of intervention components. Now when I use the term screening here, I'm using it in the sense it's used in engineering, which is to weed out poorly performing components. I'm not using it, I know in intervention science it's used a lot to screen subjects in and out of a study, and you might also want to do that. But that's not the purpose. So I'm calling this a screening experiment because it's supposed to screen out the poorly performing components and screen in the ones that are working well. So you want to weed out underperforming components. You want to get a sense of the magnitude of each component's effect, because that's going to be important for deciding whether or not you want to include it, and also to get a sense of whether the effect of a component is in some way dependent on or influenced by the presence or absence of another component. Any experimental design is a possibility for inclusion here, or for use in most. The only requirement is that it's selected based on the resource management principle. That's the only requirement. So to select a design, you want to consider several different alternatives and examine what scientific information each one will provide and whether it's what you want. Different experimental designs give you different scientific information. Sometimes it's very subtly different, but it's different. And so you need to think about that and what each design costs in terms of number of subjects and number of experimental conditions. Usually those are the two. Usually the costs can be divided in this way: the costs associated with subjects and the costs associated with experimental conditions. And again, the starting point is the resources that you have. So let's review the design alternatives that we considered for the opt-in study. So we could have conducted a separate experiment for each component. So that would have been one experiment comparing 12 coaching sessions to 24, a second one comparing no text messages to text messages, and so on. And I've seen people do this kind of thing, where they're interested in individual intervention components, and they just do a separate experiment for each one. This is a design that is used sometimes in intervention science, where there's one control condition. So in this case, it would be everything set to low, and then one condition where people get 24 coaching sessions and everything else is set to low. A second condition where people get text messages and everything else is set to low. A third condition where these people get only PCP communication and everything is set to low, and so on. So each of these is a treatment condition, and then this is kind of a shared control condition. It's often called a comparative treatment experiment. There's similar designs that are sometimes called dismantling designs or additive designs. They all have the same statistical properties. Third possibility is a factorial experiment. So in the opt-in study, this would be a 2 by 2 by 2 by 2 by 2, or 2 to the 5th factorial experiment that would have 32 experimental conditions. So let's stop there. There actually is a fourth alternative I'm going to talk about in a second, but let's look at the resource requirements. 5 individual experiments would take about 2,800 subjects and would require 10 experimental conditions. The comparative treatment study would require about 1,700 subjects and about 6 experimental conditions. The factorial experiment would require only 560 subjects. And I don't know whether that's a surprise to any of you, but a lot of intervention scientists seem to feel that, and this is I've noticed a pervasively held misconception, that factorial experiments require huge amounts of subjects. And it's kind of ironic because the opposite is actually true, that factorial experiments, when properly analyzed, actually require many fewer subjects. And in fact, this is why they were invented to begin with, because they're very economical in terms of use of experimental subjects. The downside is that they usually require many more experimental conditions. So 32 experimental conditions would be required here. Let's look at interactions. Now, interactions can mean, in the intervention world, can mean a couple different things, both of which are potentially interesting. So you might be interested in seeing whether there are moderators of the effects of the components. So, for example, is gender a moderator of the effects of the components, or education or reading level or something like that? You can do those kinds of analyses with the designs I'm talking about, and we can talk about that more during the discussion if you're interested in it. That's not the kind of interaction I'm talking about here, though. Here I'm talking about interactions between components that we're examining. So, for example, does having your buddy trained make it more likely that meal replacement will be successful with you? That's the kind of interaction I'm talking about. You cannot look at those with the first option or the second option, but you can look at interactions with a factorial experiment. So we did this, and then Bonnie said, well, I don't think we can handle more than 16 conditions in the field at one time. So what do? There is a fourth alternative, the fractional factorial experiment. This is a special type of factorial experiment. It's used routinely in engineering, but it's very rarely used in intervention science, or even in the behavioral sciences at all. In a fractional factorial experiment, you run a fraction like a half, and that's the design I'm going to show you, is a half fraction of the experimental conditions. A fractional factorial experiment is powered exactly the same. It uses the same number of subjects overall as an ordinary factorial experiment, but it just has fewer experimental conditions. So there'll be more subjects per condition because the overall N is the same. But there are some important trade-offs that I want to make you aware of. So we ended up settling on this fourth option that required 560 subjects to power, but only required 16 experimental conditions. And that was a substantial savings. And we can look at interactions, but not all of them. So this is the opt-in design. This is the opt-in design. So the overall N is 560, 35 per condition. Now, those of you who are kind of steeped in the RCT tradition might be thinking, how could it possibly be sufficiently powered with only 35 per condition? But in a factorial experiment, the power is driven not by the per condition sample size, but by the overall sample size. And I'm going to show you why that is right now. So let's look at, well, first of all, let me just point out that everybody got this core intervention. And then we were manipulating these variables. So let's look at the main effect of phone coaching. We're going to get the main effect of phone coaching by comparing the mean of conditions 1 through 8 versus the mean of conditions 9 through 16. Okay, the mean of the people who got 12 sessions versus the mean of the people who got 24 sessions. Fine. But now let's look at PCP communication. The main effect of that we get by comparing the mean of the people who got yes, who did get PCP communication, versus the mean of the people who did not get PCP communication. Same thing for text messages. The mean of the people who did not get text messages compared to the mean of the people who did get text messages. Each of those comparisons is based on the whole N of 560. This is something that is I think, very cool about factorial experiments, is that it's kind of like recycling subjects. You don't use them to estimate one effect and then throw them away. You use them to estimate a number of different effects. And so this is why factorial experiments are so economical in terms of use of subjects. You just get, you get a lot of mileage out of each subject. Okay, now I said this is a fractional factorial design, and as you all know, I'm sure there's no free lunches in statistics at all. And so when you gain the economy that goes along with, yes?
Were there anybody that only got the core got not, because it was a beautiful explanation. Anybody did not get but just the core?
That's a really great question. If this was a complete factorial, yes. And in some other factorial, some other fractional, there's a lot of different fractional factorial designs, could be. But in this one, no, we do not have a design. We do not have a condition where people got absolutely nothing. The closest, I think, is this one, where there was a PCP communication and they have a low level here. Well, they have PCP communication, but they're low on all the others. And that's an interesting feature of fractional factorial designs, that you don't necessarily need a condition where people get nothing. And the reason is that in any factorial experiment, you never pull out one condition and compare it directly to another. So there isn't a control condition, one single control condition. So you don't really need that. Yeah.
So just for Milton's point, if it is desirable to have a no, I guess, intervention condition, there are two, in a sense, equivalent replicates of the fractional factorial design here. So we could just rename the PCP complications.
You could.
Yes, just make them no. And
just switch that. You could just.
Then we have the
that. You could just because it's. Yeah, that's a really good point. It's arbitrary. What's the high level and what's the low level, essentially.
One more question, then we go on. And
just a comment. Core intervention can usually be called the standard of care.
Mm-hmm.
And so it allows for that. So if you're doing standard counseling, it's
sure, absolutely, yes, absolutely, yeah.
Okay, let's go on.
Okay, sure. Okay, so in this fractional factorial design, we have gained economy by only running half of the experimental conditions. And so to look at this one way, let's say we decided we only had 16 experimental conditions that we could run. Our choices are to run this fractional factorial design that enables us to look at 5 factors, or do a complete factorial with only 4 factors. So the trade-off here is if we, given the resources we had, we could have run a complete factorial with 4 factors or fractional factorial with 5 factors. So we chose the one that gave us the ability to look at 5 components, but whenever you start pulling conditions out of a factorial experiment, certain effects are estimated as a bundle with certain other effects, and that's called aliasing in statistics. And that's undesirable, right? but it's a trade-off. It's a deliberate trade-off that we made here. This design is called a resolution 5, and what that means is that each main effect is aliased. In this case, it means each main effect is aliased with one 4-way interaction, and each 2-way interaction is aliased with one 3-way interaction. So when we estimate a main effect of a component, it could be due to the main effect of the component, or in theory, it could be due, at least partially or even completely, due to a 4-way interaction. But our theoretical model, and we spent a long time talking about this, does not predict large 3-way and 4-way interactions. So if you're willing to assume that the higher order interactions are negligible in size, they don't have to be exactly 0. They just have to be negligible in size. Then it makes sense to take advantage of the economy offered by fractional factorial design. This is one reason why I really emphasize the theoretical model. If your theoretical model predicts that there's an important 4-way interaction, then you should not use a fractional factorial design. If it doesn't, then it's something that you might want to consider. So let's just take a look at these trade-offs, because this is kind of the logic of the resource management principle. You could choose to do a complete factorial experiment that would enable you to look at 4 components. You could do what we did and choose a fractional factorial experiment that would enable you to look at 5 components. So looking at 5 is better than 4, right? In reality, the higher order effects could be negligible. So in order to use this fractional factorial design, we had to assume that the 3-way, 4-way, and 5-way interactions were negligible in size, particularly the 4-way and the 5-way interaction. Or we could be wrong, and there are some large interactions there. So let's take a look at the costs and benefits. If we had chosen what many people would call the safe alternative, which would be a complete factorial experiment and sacrifice looking at the 5th component, if the higher order effects were in fact negligible, that would have been a waste of resources, because it would have meant that we could not look at that 5th component. However, if we were wrong, then we would have been moving science forward faster by taking that safer route. If we choose the fractional factorial design and the higher order effects are in fact negligible, we move science forward faster. If we were wrong and some of the higher order effects are large, there is a possibility of some incorrect decisions about component selection. Sometimes maximizing efficiency calls for taking calculated risks. Before I mentioned, sometimes you have to take calculated risks. And this is an example of where we decided to do that. I'm not saying that this would be the right decision in every circumstance. I'm just kind of using this as an illustration of the thought process. There are opportunity costs associated with a less risky option. So there's a risk here, but some people would call this less risky, but there is the possibility of wasting resources here. So this is the resource management principle, is working through this kind of conundrum. Okay, so we don't have any data yet. We're in the field with this experiment, but once we have it, we'll conduct an analysis of variance, obtain estimates of the effects of each of the components, and based on that information, we'll select the components to include in the optimized intervention. Okay, so let's try and imagine the state of the art. This is going to be kind of a commercial for most. Let's try to imagine the state of the art in HIV behavioral interventions if people were using this approach more widely. So interventions would include known effective components. So that would reduce unnecessary participant burden. We would have leaner and meaner interventions. Every intervention would be immediately scalable because you do what I said before was starting from the end. You would identify important implementation constraints and then optimize the intervention to operate within those constraints. We would know which intervention components work, so interventions would be transparent, and a coherent base of scientific knowledge would accumulate. So other people would look at other people's work and say, okay, they found that this approach works, this approach works, this approach works. We don't have to look at that again. Now we're going to test another set of components because we'd like to add more components or possibly replace replace some components to make a better intervention. Once you have an optimization criterion, you've set a bar. So let's say you developed the most effective HIV prevention intervention you can get that costs less than $500 a person to deliver. Someone else can build on your work, or your future work can build on your work to say, well, we are now going to develop an intervention that still costs $500 a person, but is more effective than that last one. Or we're going to develop a new intervention that is equally effective but cheaper. You see what I mean? So this is what I mean by incremental progress. So then I would hope that there would be incremental progress over time, which is something I feel like we're not getting, at least not very quickly in intervention science. Seems like everyone is developing new interventions, but it's not clear, and they're different, but it's not clear how one intervention is better than another. So there'd be incremental progress over time, and then interventions would steadily gain impact in the fight against HIV. So this is my website, and there's a lot of information there about MOST. And there's even a section that has advice for people writing grant proposals involving MOST. Well, yeah, and there's actually a few paragraphs in there that you're welcome to, pull out, and it's not copyrighted, so take it and use it and amend it as you see fit. It can be hard if you end up landing on a factorial experiment, and factorial experiments very often turn out to be the most efficient and cost-effective way to do this experimentation, but it can be hard to explain them in a grant proposal. So I've got some language in there that's worked okay for me. This is the Methodology Center's website, methodology.psu.edu, and of course there's my section of the website, but you might be interested in my colleagues' work too. I have a lot of amazing colleagues who are doing methodological work in a number of different areas. And there's just a few articles, and I'll leave the slides here. There's also a reading list on the website. Thank you.